This painting by Joseph Wright shows a demonstration of an orrery, a moving model of the solar system. Orreries became very popular in the 18th century, and this was because of the public fascination for the universe which had been sparked off by the work of Sir Isaac Newton and his followers. This orrery was made by George Adams, the leading instrument maker in London, in about 1790.
This instrument is a very versatile astronomical teaching kit. It can be used in a variety of forms. At present, it's arranged as a planetarium, showing the entire solar system. And by the entire solar system, I mean the system right out to Uranus, because this instrument was made later than the discovery of Uranus by Sir William Herschel. So it not only has Saturn and all her satellites, but Uranus and the 2 satellites discovered by Herschel. But it isn't only a planetarium. In fact, you can take off this entire section, and in its place, you can substitute this piece of apparatus, which is called a tellurian. When you turn the ivory handle with this in place, the Earth rotates, and it demonstrates the changing seasons and the diurnal rotation of the Earth. In its place, you can put a attachment called a lunarium. And as you turn the handle, in that case, the moon moves and it shows the lunar cycle. All the astronomy involved in this instrument isn't in any real sense Newtonian. It really, there's nothing here which isn't in Copernicus, say. But in the 18th century, it would have been billed as a Newtonian instrument. It would have been seen as part of a course in Newtonian natural philosophy and astronomy.
During the 18th century, a whole Newtonian culture developed. But most of the work which made Newton himself famous goes back to the 1660s when he was at Trinity College, Cambridge. The little hut tucked into a corner is said to be Newton's laboratory. In 1665, there was plague in Cambridge, and to escape it, Newton fled back to his family home at Woolsthorpe in Lincolnshire. It was during the time he spent here that he made some of his most fundamental discoveries.
He told us himself that it was then that he first formed his new theory of light and colour, then that he had the first ideas of a new sort of mathematics, the calculus as we call it now. He called it the method of fluxions, and finally his first quite simple ideas of what was later to become the mechanical theory of planetary motion and the theory of universal gravitation.
Newton's fame derived mainly from 2 books. The first is known as the Principia, the mathematical principles of natural philosophy, which puts forward principles underlying the entire universe and the forces which govern it. Chief among these was gravitation, and Newton's calculations included the force of gravity keeping the planets in their orbits and the path of those orbits, which he confirmed to be elliptical. The second book was Optics, which largely derived from his experiments on light and colour. But Newton's use of experiment was rather different from that of his predecessors.
In the 17th century, the masters of experimental philosophy, such as Robert Boyle, Robert Hooke, reckoned that there were 2 kinds of problems which experiment could solve. Experiment was the way in which one made matters of fact, which were unchallengeable. And then on the other hand, one was allowed to erect what they called hypotheses, which would explain the causes of these facts. Now, in both of Newton's great published works, the Principia and the Optics, we find experiments, but these experiments are designed to aid the structure of what he hoped would be a universal mathematical theory.
Newton's work on light arose from his practical experience with telescopes. In Newton's day, telescopes were made with lenses, as they always had been, and the lenses were ground by opticians.
Now, Newton was working with instruments such as these. These instruments are commercial telescopes that you could simply go and buy in an optician's shop, such as the shop of John Yarwell. And we know that Newton had associations with one or two London opticians, and that he was interested in grinding lenses and so on, and producing his own telescopes. But there was a great problem with 17th century refractors, that's to say telescopes whose optical components are lenses, glass lenses. Instrument makers, in this case optical instrument makers, could only grind spherical lenses, that's to say lenses whose contours were sections of a sphere.
There were two problems with these lenses, a blurred image and coloured edges. It was this problem with colour which Newton decided to investigate.
In Newton's interest in refraction and colour, he chose to work with prisms such as this one, because it's a lot simpler than working with a telescope. This is a prism of the kind that one could readily buy as a toy in England at the time, and we know that Newton, in fact, began with such toy prisms such as these. With prisms, Newton was able to work on what he called the celebrated phenomena of colours. That's to say, the production of colours by the use of triangular prisms.
This work culminated in what Newton called the crucial experiment. He passed a beam of light through a prism, splitting it into different colours. He observed that each colour was bent, or refracted, through a different angle as it passed through the prism. He then placed a second prism in the path of one of the colours and demonstrated that no single colour would split up any further. He deduced from this experiment that white light consists of a mixture of different colours, each of which refracts to a different angle. Newton realized that, as in a prism, light passing through a lens would always produce coloured edges. So he developed the reflecting telescope, using curved mirrors instead of lenses. The idea was first proposed by James Gregory, but Newton was the first to build one, and an example was demonstrated at the Royal Society.
This extraordinary little thing so impressed everybody because you could see the satellites of Jupiter and so forth. It so impressed all these people in London, including King Charles II himself, that Newton became, so to speak, a lion almost for a few years. And then the Royal Society induced him to impart the theoretical ideas which had led him to attempt the construction of this new form of telescope.
In Newton's telescope, the image is reflected by mirrors to an eyepiece at the side. But in the 18th century, reflecting telescopes were also made after Gregory's design.
This is the typical amateur telescope of the 18th century. It's the kind of thing that you would find not in a professional observatory, but in the library of a gentleman who's interested in astronomy and natural philosophy. This one was made by a man called John Cuff, who was an optical instrument maker in 18th century London. And you can see, if I take a component of one of these telescopes, this is the objective mirror. You can see there's a hole in the middle because it's what we call a Gregorian construction. In other words, when the mirror is in the tube, the light is coming down from the star. It's reflected from this mirror back to a secondary, reflected again down the tube, and through the hole in the center and into the eyepiece. One of the amateur astronomers who was conducting astronomy with telescopes, reflectors of this sort of size, in fact went on to become a very celebrated astronomer indeed. And that was William Herschel. Now, Herschel began with Gregorians and Newtonians of some 5-foot focal length and so on. But because he was interested in very faint and very distant objects in the sky, such as double stars and nebulae and so on, he went on to build very large telescopes. Now, this is a 10-foot telescope by William Herschel. In 1781, he noticed an object in the sky at a position where he didn't expect to see a star, and whose appearance clearly wasn't stellar. In fact, he began by thinking it was a comet. But it soon became clear from the orbit of this body that it was in fact a planet. Now that was an absolutely extraordinary discovery in the period, because since the dawn of written astronomy, we'd known how many primary planets there were, and here was a completely unknown amateur observer working in his back garden, essentially, with homemade telescopes. He had discovered another one.
The astronomers at Greenwich, Paris, and the other big observatories were not interested in exploring the universe. Their main concern continued to be the precise measurement of star positions and the development of accurate chronometers to solve the great problem of navigation, the determining of longitude at sea. Sailors measured moon and star positions with portable sextants and other instruments and checked them against the new charts.
But of course, all of this had an important spin-off for the theoretical Newtonian program, because as increasingly accurate measurements were made in the professional observatories, they could be applied to the ever more detailed application of Newtonian celestial mechanics. So that as the 18th century progressed, people became ever more confident that the Newtonian gravitational theory was in fact accurate to a very precise degree.
One of the principles of Newton's gravitational theory was that the force which makes an apple drop from a tree is the same as the force which keeps the planets in their orbits. And he worked out the mathematics to support this theory of universal gravitation. Gravity became a popular subject for experiment and demonstration in the later 18th century. In this Atwood machine, slightly different weights are suspended over a bearing. The heavier weight is placed on a platform. The pendulum acts as a timer and releases the weight so that you can time the fall over a particular distance. Newton's observation of gravity on Earth had grown into a theory for the whole universe.
Newton also believed firmly that all bodies in the universe are acting upon each other all the time by means of forces, a variety of forces which bring about a variety of effects. The force of gravitation is, of course, the force which, as everyone knows, he studied in great detail in the Principia as it applies to the planets and the tides and the shape of the Earth itself.
Newton's theory that gravitation would affect the shape of the Earth was put to the test by members of the Paris Academy led by Maupertuis.
What Maupertuis and his allies in the 1730s did was to claim that Cartesians supposed that the Earth was flattened at its sides, whereas Newtonians supposed that the Earth was flattened at the poles, so it was shaped like an onion rather than a melon. And this, therefore, according to Maupertuis, provided a crucial test between Descartes and Newton's ideas, between the theory that there is a whirlpool or vortex moving swiftly round the Earth, and Newton's idea, which is that there is universal gravitation. So in the 1730s, by skillfully lobbying the Navy Ministry and the French government, Maupertuis engineered expeditions both to Lapland, near the Arctic Circle, and to Peru, near the equator. Both expeditions took about 5 or 6 years. That was massive public investment. And both expeditions measured the length of 1 degree. By comparing the difference between these measures, it was possible to determine the shape of the Earth, and Maupertuis reckoned that the expeditions showed that the Earth was indeed flattened at the poles and that Newton was right. Maupertuis' friend, Voltaire, commented rather wittily that you found in really boring places what Newton knew without leaving his room. And it's that kind of, as it were, staged, managed trial which makes French Newtonianism a success.
Stage management on a more modest scale became very important in the spread of Newtonianism, with demonstrations in coffee houses and theatres. This group is watching a chemistry lecture with the burning of brimstone on copper. Electricity was a popular subject, one of the forces in which Newton had been interested.
Well, these electrostatic machines represent the kind of experimental apparatus which was popular in 18th century England. What we have here are two electrostatic generators. They work on essentially the same principle, but the design is a little different. They represent the two common designs of the period. One has a glass cylinder, which you turn with this handle very rapidly. It rubs against this leather plate here, and the static charge is generated, carried off through this apparatus to whatever your experiment is that you have in hand. I mean, you could produce sparks, bigger, longer sparks. You could electrify people even. You could produce electric shocks. Everyone could join hands and all be shocked together. So that the idea was that through spectacle, you could learn something about Newtonian natural philosophy.
Here we see the emergence of an experimental Newtonianism, in which flashes and bangs are displayed before polite but fee-paying audiences. Natural philosophers here could ply their trade by charging guineas for series of 12 or 24 lectures on what they called the Newtonian system of the world. They would show electric machines, they would show Newton's optical experiments, they would kill animals in air pumps to show the vital force contained within the air. They would demonstrate extraordinary fermentations, all this to show the Newtonian doctrine of active principles, and in particular to show that these active principles had been impressed into matter by God. In that sense, crucially, a natural philosopher was like a priest, because he was performing a semi-divine office of demonstrating for his audience the presence of God in nature.
One might say that for Newton, the universe was not only the artifact of God, it was not only God's creation, but it was perpetually maintained and kept in due order by God's action in nature. So that in his view, and in this respect is very different from the view that came into being during the 19th century, the universe was through long eons of time essentially unchanging. It always had been as it is now, and always would be as it is now when you consider things on the large scale. For Newton, this intervention of God in the working of nature was, of course, of supreme importance.
French Newtonians took quite a different view of God. This is the frontispiece of an influential book by Voltaire called The Elements of Newton's Philosophy. Like most of the French philosophes, Voltaire only accepted God as the creator, not as the maintainer of the universe. Voltaire did more than anyone to popularize Newton in France. But for the elite, the great demonstration of French Newtonianism was the 28-volume Encyclopédie edited by Diderot in the 1750s. It covers a vast range of human thought, much of it inspired by the ideas of Newton, Bacon and Locke, brought together under the banner of Enlightenment philosophy. Even the section on mathematics covers a wide field. Some of Newton's optical experiments are included, as you might expect, but it also covers various aspects of craft and technology, a major concern for the Encyclopédie, derived more from Bacon than from Newton. This is a workshop making mathematical instruments. Significantly, it was the mathematician d'Alembert who wrote the important preliminary discourse to the Encyclopédie.
It poses as a history of the arts and sciences since the time of the ancients, but in fact it's a manifesto of the encyclopedia, and it puts Newton, Bacon and Locke at the center of philosophical concern. What's important about d'Alembert's argument is that he walks a tightrope between what one might call rather loosely English empiricism and French rationalism. He makes Newton, Bacon, and Locke look like the trinity of the new philosophy, that they've combined together the deliverances of reason, which here of course means mathematics, and the deliverances of experience, which means the experimental philosophy.
Above all, it was principally the French who spread Newtonian ideas across Europe. They achieved this by the various editions of the Encyclopédie and through the travels of the French philosophes themselves to Switzerland, Germany, even Russia. But as the Encyclopédie demonstrates, all sorts of ideas were labelled Newtonian, including some which Newton himself would not have recognized. So is it possible to think of Newtonianism as a coherent phenomenon at all?
I think one way to think about the culture of Newtonianism in the 18th century is to distinguish between two kinds of places where natural philosophy is pursued and consumed. One is the academy and the court, where the key sciences are rational mechanics and celestial mechanics, where analysis is developed, and where science is pure and abstract and pursued by an elite of mathematically expert philosophers. There, Newton stood as the supreme discoverer of the mathematical principles of natural philosophy, and the Principia as the greatest work of science. Lagrange allegedly regretted the existence of Newton's Principia on the grounds, he said, that there was only one world to discover, and Newton had discovered it. So that creates one notion of Newton as the master mathematician and the author of a science appropriate for the court. But then over against that, the other ideal site at which natural philosophy is created and performed is the coffee house, the lecture room, the theatre indeed. So these two cultures, the culture of the academy and the culture of the theatre, represent two quite different ways in which Newtonian natural philosophy became part of the popular culture of the 18th century.